This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
People who aren't familiar with how these big, especially National Science Foundation projects come together is like, this doesn't happen overnight, right? Like it happens because of a sustained investment in world-changing research over decades to produce the types of institutions where people like yourselves can come up through PhD programs and be apprenticed as professors and do smaller scale tests underneath other professors, guidance and mentorship, and meet each other at conferences. You know, I mean, you're from different places in the country, right? And then propose something 10 years ago that is now coming to fruition. And so, you know, this is the reason when we talk about, you know, a 5-year funding cycle for things like NARI, all the experimental sites in the NCO, like that's why, because we can't do these types of tests if you don't have the security, the predictability, the certainty that this is going to be here 10 years from now.
These are long through lines that have an incredible amount of involvement. I mean, we have huge involvement with industry over that same threaded line over 10 years at a variety of levels as well. And so everybody has to be able to believe that when you begin that journey that you'll complete it and participate in the whole way. It's amazing. Tara can speak to the partners of for CFS10. It's beyond imaginable how many different people, organizations at all levels have helped make this happen.
Yeah, it's pretty amazing too. Like, you know, even with the level of you know, support, funding, involvement from industry partners, this isn't something that one company is just going to fund by themselves, even if they could, but their shareholders would crucify them. It's, you know,
or one agency either.
Or one agency.
It's not a one agency, like Ben said. You know, it's a couple of investigators with some passion about something, but you know, you know, when you really put the wheels down on the ground and you try to you know, generate some movement forward, there's lots of little steps to get there, even though you had a little nudge in the beginning, a little bit of, you know, support. It's not even one agency. It's not even the National Science Foundation. It's not even, you know, we've got sponsorship from so many agencies, but it's not any one, you know, it's many different ingredients for these very large scale landmark programs and other programs that have benefited from the use of NERI facilities. No matter how large or small, they generally embrace and need the support of many different partners.
Yeah. Yeah. And but let's talk about some of the exciting stuff here, about some specific aspects of the cold form steel frame buildings. For people who aren't familiar with that at all, like, why is that important? We've talked a little bit about, you know, being able to put these together in modules and panels. What are some other exciting things for people who are our non-civil engineering friends who we definitely appreciate?
Yeah, I can start us off. So, I mean, it's generally regarded as a very efficient, dimensionally stable form of construction with a lot of promise for fast, resilient construction. We've been working on aspects of that to make it faster. That's why we've been in this collaborations with building as whole volumetric units, like, you know, as modules, like you see floated above Tara. It's a non-combustible, so I mean, obviously it's steel and cementitious products or whatever. So that's certainly a feature. So its speed of construction and its lightweight are its primary, you know, sort of drivers that give it an excitement for a lot of us. CFS10 is just kind of pushing the envelope on all those things. So the building that, you know, is behind you there is beyond code limits. It has systems in it that an engineer couldn't ascribe to use today because they were based on research, and so they're in there as a concept that has been tested at the component level, but will be tested at the system level for the first time. So there's a lot of features of the actual building construction that go beyond what you can do in cold form steel today, which is the whole point.
Yeah. Let's pull the thread on that a little bit. Like, what's an example of something that's like you couldn't build this today because it's above code? Like what are some of those geometric features?
I mean, the simple
Just go
one.
above your forehead. Just go
Yeah.
above your forehead.
Yeah.
The code limits us to 65 feet or 6 stories in zones of moderate to high seismicity. So the engineer will open up the design code and they cannot use a lateral force resisting system of CFS above your forehead. So for reference, the orange towers to your left. And
Somewhere
yeah,
over, yeah.
and this photo I chose is just getting us above there, just trying to stretch us above that code. So just wanting to design something that would have to be in a moderate to high seismic zone above that elevation, it wouldn't be allowed. Designer wouldn't be able to do that. But lots of really good component tests on shear walls and their ensuing components, whether they're in a single wall line or multiple walls put together, have shown that these types of structural wall brace systems can handle the loads that come about under this scenario. And so, like Ben was saying, we can do this at the component level. We can do it with models, and we think we can build it, but we've already broken ground by constructing it on a shake table. And actually, that building was subjected already to an earthquake because we had a magnitude 5.2 earthquake event that we captured a few months ago, and we had
Yeah.
sensors already installed. So we,
That
we
was
already know that it's doing great.
that was really interesting. I remember talking to Courage, the facility manager down there, was like, well, we already had our first test and it was real life and it worked great.
We were isolated from it though, because thankfully we were below the shake table. I had a student on the roof who was working on
Ooh,
rooftop equipment, but we were isolated and below the shake table. So
that had to be exciting.
funny enough. Funny enough. Yeah.
Yeah. I've only been through one earthquake myself, and it was a really really minor one out in Connecticut, and it felt like someone was carrying a refrigerator or something next to my desk. It was like like that was weird, but yeah, never something like that. You make an interesting point of like, okay, code only allows you to go so high and moderate to high seismic areas. There's areas of the country that don't experience seismic events regularly, but could and will someday experience a seismic event along the New Madrid Fault. This looks like a great application for places like that. Yeah, it looks like a normal building. It doesn't have all these isolation features that you may need out in California, but it will still, well, hopefully, pending all the tests, hold up to that when it happens. And so you can kind of get around the mental gymnastics of, well, we don't really need to build for seismic stuff because we're in Indiana, but you get the benefits of that as a byproduct by building it with an efficient way of construction.
Yeah, absolutely, Dan. And so, you're talking about sort of what changes. So as you go taller, you add more gravity load because you're just adding more stories. And whether it's wind because of exposed area or seismic, because you pick up more lateral load, particularly at the bottom of the building. And so that's the other sort of key thing that goes beyond the code is if the engineer would sort of look up and design in cold form steel, it's been pretty prescriptive for that lateral design. So, design it this way, use these fasteners with this spacing, et cetera, and that's a table, and they look it up and they're good to go. But both having an improved calculation method, but also having some tables that would go quite a bit beyond the strengths that they have now, but still using cold form steel has been what a lot of the sort of first phase and early work did. We keep calling it component tests or shear wall tests. It was moving the strength window out. So from a strength standpoint, that's really all you carry about for wind. So you go someplace where wind is mostly controlling, you've dialed in the strength, you're generally pretty happy. You got a lot of details around the envelope for that hazard, but that's really sort of your primary thing. But for seismic, we care about a lot more, right? Proving out that we're happy at the component level and then at the system level of what happens when we really push and we go past sort of peak strength on these elements is really what's exciting about the earlier component research and then this big system research. And really, is beyond what an engineer can utilize or specify today for what's in the codes.
Yeah. And you make an interesting point of going back to the component level testing. I mean, you've used other NERI facilities like Lehigh University, the Atlas Lab for that still uses very large components that you can test there. And then bringing it all the way to the system level. Now you're at the UC San Diego Outdoor Shake Table, funded by the National Science Foundation to be from that single degree of freedom. Now it's 6 degrees of freedom, so you can go up, down, left, right, heave, yaw, pitch, roll, all those fun things. What makes this different, and what does this facility make possible?
I can tackle that because I've been here through the unidirectional and the multi-directional
Yeah, you've been
kind
there
of
a while.
program, and yeah, I finished my PhD when they started the idea for this facility. If I go back, but then I wasn't here. I was at another UC, but then slowly kept making my way south, and finally found my way here. And there was a wonderful facility here for the community to use. At that time, it was part of NEAS, of course. It was a unidirectional table, and actually part of this program did utilize the unidirectional capabilities of the facility. Just before the facility closed down for its upgrade activities, we were able to conduct a whole suite of different wall line tests on CFS systems. We have one student that worked on that and complemented some of Johns Hopkins team's efforts on the modeling side. And so that was a really great springboard into understanding CFS, steel sheets, shear walls, and wall lines, and finishes, and openings, and other things that kind of give us a lot of information for this program. But this facility is just so unique. I mean, I was saying the nation and in the world, it's outdoor. It's, as you mentioned early on, got really reasonable climate. So, I mean, I'm shouting our blessings this year, 2023, when I worked with the Tallwood team. We had a very, very 2022, 2023, we had some of the wettest winters in history. But we've been quite fortunate with the timing of this particular program. Lucky so as well, because we have finishes. We've incorporated finishes. You see some of the finishes in the diagrams or the photographs behind us. And that was a really important element for us to aim to integrate. We know that because of the lightweight nature and the addition of finishes is going to be needed. That is gypsum to finish it. Exterior finishes, one of the most common is like a cementitious, you see cementitious type product, and the obvious weatherproofing and other things on the exterior of a building, for example. We have one face of the slice of this building that actually has those types of finishes. So here you can apply those and you can attach those kinds of things to real building systems and make them of quite high fidelity when you're on an outdoor table such as this. So that's really a great opportunity to test in our moderate climate. But now we're at the potential to be able to utilize the multi-directional earthquake shaking capabilities of the table. But to put it in perspective, our building only uses about less than 10% of the facility's vertical payload capacity, despite the fact that it's extending above your head there. So there's really a tremendous potential to load the shake table up with heavier specimens. We can also we've had colleagues that have extended the platen outward laterally and utilized the reaction mass in that regard. So a lot of great potential for us. Another aspect we're able to incorporate in our program is the concept of secondary hazards following earthquake shaking. I think Ben alluded to it earlier, and we've got a whole team that's going to follow us following the earthquake sequence and conduct a variety of live fire scenarios. So in the event that a live fire breaks out within a building, it's a real potential to happen due to gas lines and other triggering sources. We're going to try to recreate those on this particular specimen. And you couldn't do that you could, but you'd have the obvious, spatial situation within the building that you're in. But you can do that on this outdoor facility if you, obviously, if you take the appropriate safety measures. And we've had,
we've
had some experience. Yeah. We've had some experience with that, and so the site is trusting in us, and we have the safety precautions courtesy of San Diego Fire Department, and it's and it's fire trucks that'll be on site during those tests.
Yeah, and the whole team has done a great job of making things as close as you can to your original schedule. So you're right before the peak of fire season for that, and just done a really great job managing it.
Thanks for listening to today's episode of Design Safe Radio. This show is sponsored by the National Science Foundation, grant number 2129782. You can subscribe to Design Safe Radio on iTunes, Stitcher, or wherever you find your podcasts. Please leave us a review so that we can improve the show and also help others find our episodes in iTunes. Thanks for your feedback and support. We really appreciate it. You can find out more about NARI at designsafe-ci.org, on Facebook at Design Safe Radio, or on Twitter at NARI Design Safe.